So the alternate series estimation theorem is great for estimating estimating the sum and finding the error of an alternating series. Now what if we had a non-alternating series? Oh, why do I always have this color? What if we had a non-alternating series? What if we were just given any series where all its terms were positive? Is there a way for us to estimate the sum? And the answer is undoubtedly yes. I'm sure at some point there was a doubt, but somebody invented this, and it's what we call it's an extension really of the integral test. And I say that if we know that the sum converges, then we should be able to find, if we know that the sum converges and we want to estimate the sum of this, all we have to do is take the first finite terms that we want, and we can find effectively, like the alternating series estimation test, we can also find the quote-unquote error bound of it. And this test works also pretty intuitively. Basically what we have is, imagine we had a series, let's say an equals to 1 over n squared. What we do is we would transform our discrete series into a continuous function. So this would undergo a transformation, and we would say, let's let f of x equal 1 over x squared dx. Or there's no dx, sorry. And once we do this, we can then graph our integral, I think. And since x is constrained to be between, I guess in this case, from n equals to 1 equals to, so since x belongs to 1 and infinity, we don't have to worry about the negative portion of the graph. And at this point, we'd say, well, so our sum would be sum equals 1 to infinity. So we'd say, well, let's not sum from 1. Let's actually sum from 3. Because 1 is not a number that works out for me. Because then you were dividing by 0. And that is rough. So let's say we sum from n equals 3 to infinity. We can say that this is equal to the sum from, we could have started from 1. That's okay. Back to 1. I have made a mistake. Back to 1. We are not dividing by 0. 1. 1. 1. We can say that this is a sum from n equals to 1 to, let's say, 3. This is why I had meant to put the 3, of 1 over n squared plus the sum of 1 over n squared. So we know exactly what this is. We know that this is equal to 1 plus a quarter plus a ninth. Now what we want to find is our error term. This we can know as our error. And we want to find the maximum value, well, maximum and minimum value of this error. So we have a sense of where our true sum is. And to find the maximum and minimum value of this, we're going to plot this graph onto where our function is. And so let's say we start from 3. So let's pretend this is 3. and 1 over n squared to the 3 is of this value. Is it this value? This is not this value. We're not counting to 3, we're counting to 4. Yes, otherwise we'd be double counting 3. So actually we're counting to 4. So the sum is equal to n equal 1 to 3 of 1 over n squared plus 4 to infinity. So we have all the terms exactly once. Of our sequence at n equals to 4. And at this point, we can, if you guys remember Riemann sums, we can draw this rectangle one of two ways. We can extend it to the right, or we can extend it to the left. And so let's consider the extending to the right case for now. Well, if we draw these rectangles, so this is 5, and so on. And it becomes intuitive, or not intuitive, but it becomes increasingly obvious that every single term of my series, so this this rectangle is the series, and this continuous line is is the function, and it becomes increasingly obvious that my function, so if we start from here, that the area under the curve of my function from 4 to infinity of 1 over dx is always going to be less than the integral from, not the integral, it's always going to be less than the sum from n equals to 4 to infinity of 1 over n4. Because every single one of these rectangles is larger than the function, which is pretty cool. So we can say that the sum is at least this number. While interesting, it's far less helpful than the other comparison we're about to make. Because yes, you know your lower bound, but your lower bound doesn't particularly tell you, doesn't tell you too much in terms of where the series may land. So at this point, let's see if we can make a comparison for the upper bound. So once again, we draw a graph. So considering the other case, if we have a function, so same function of 1 over x squared, and now so we also start from 4. Now let's consider instead of drawing these rectangles drawing these discrete points as rectangles to the right, we're going to draw them as rectangles to the left. And it becomes obvious that my series is always going to be smaller than my function, as indicated by this shaded bit. But it's not smaller at my function if I'm taking the integral from 4 to infinity. It will be smaller than my function if the area under my curve has to include this portion. So this chunk of my function I also need to include. And so from here I know that my series will always be less than 4 minus 1, because this is 1 left, which is actually just 3, to infinity of 1 over x squared dx. And so now we know the upper bound and lower bound for the sequence, for the series, which means we have an we have a lower bound for the error term to approximate this to approximate this series. And obviously, as we can see, well, actually, this one is not obvious. So let's compute both of these to make a slight point. If I computed this, I would get what I'd get 1 over 4 actually. Yes, 1 over 4. So I know that this would be less than 1 over 4, and this would be greater than 1 over 4, and this would be less than 1 over 3. Sum of n equals to 4 to infinity of 1 over n squared. However, as we increase the number of terms we approximate our series by, this number, so for example, if we were to increase this number to 10, we would start our error term from 11, and when we start our error term for 11, our error term will actually be bounded by 1 over n will actually be bounded by 1 over 10 and 1 over 11, which will give us a more accurate, which will reduce our error and give us a more accurate estimate of our series. So one way to improve the accuracy of the estimation of our series is by increasing the number of terms we're finitely summing. And this is what's known as the extension of the integral test, and it's basically to estimate roughly what the sum of the series